All right, so we're here in the Missoula College Computer Library, and I'm sitting here with Josh Eman, and I went over a little bit this with Corey Monroe a couple days ago, but this is also going to be good for other folks who are just looking at the week 6 things for the first time. So I am going to go into week 6 resources. What we're going to do is download the system efficiency spreadsheet. I'll open it, and I will enable editing, and I will file, save as, courses, and I'm going to save it into EC 114 2015, and this is week 6. I've already done this a little bit, so I'll just call it System Efficiency Spreadsheet _BEL2. And what I'm doing here is suggesting that you keep a fresh copy and then one that you've edited. Always good, just keep a blank one and then keep the one you're working on. So if you totally screw it up, you can go back to 0. All right.
Well, you can always download one off the...
Yeah, or download a fresh one. But, okay, so here's what we're looking at. I don't have a good, I don't have my little cheat sheet pen with me, but all we're looking at here is some motor input. And this is the actual, this is the energy that is coming into the motor. So if you imagine you've got a system, maybe I will try to draw it really quick. It's not going to be pretty, but I'll draw it with a Windows journal. So all we're looking at, we got one box here, which is a motor. You got another box here, which is a belt. And then you got another box here, which is a fan. And so the belt is attached to the motor and drives a fan. And we've got power flowing in to the motor, obviously power flowing out of the motor, out of the belt, and then finally out of the fan. So energy's flowing through this thing. And we can see that the motor input is 137 kilowatts. But you can also see, if you look ahead to the spreadsheet, we're going to be running most things in horsepower. So the first thing we're going to want to do is convert from kilowatts to horsepower, and the conversion factor is given right here. So let's just do that as a quick little first exercise. And Professor Fraser's done a really nice job showing that the yellows are where the inputs happen. And he's also done a really nice job up top sort of telling you what they're going to be. So it's just more or less at this point a little bit of a matching exercise. So what we'll do is just in this cell B10 say equals 100, and then just click on 137. And that way, we could actually come up here later and say, okay, it's 150. Now it updates to 150. So the nice thing about these things up top is you're sort of allowing this little cluster of cells at the very top to affect everybody else. Okay, fine. So next thing we're going to do is convert that to horsepower. So from there, and the way I like to think about this is I know that a horsepower is 746 watts. So I therefore know that a horsepower is less than a kilowatt, which is not 1,000 watts. So the question is, do I divide or multiply? Well, you got to do one or the other. So first the equal sign in there, and I'm going to try division. 0.746, and that should make sense. I mean, it should be the case that there are more horsepower than kilowatts, because horsepower is smaller than a kilowatt. There we go. So equals dink.
Those.
7.746. Just the zero. There we go. Okay, perfect. So now I'm going to do a control 1 on this cell. The reason for doing a control 1 is so I can click on number and just get rid of these decimal points. It's just a little cleaner there that way. All right. So now I know that I've got 184 horsepower flowing into the motor. Now, back to the diagram. The motor is going to have some efficiency. I'll just call that eta sub m. So that's the Greek letter eta, and it's kind of a nasty looking M, but that's what it is. And here I can just put in equals 0.93. That's already given. So we know that we're losing 7% of our power in the belt. So in order to figure, or sorry, no, I'll take that back. The motor itself is 93% efficient. So we know that of the 184 horsepower coming into the motor, I can just write the 184 right here. 184. And we know if the efficiency is 93, that'll tell us how much power comes out of the motor and how much is delivered to the belt. So just equals dink times dink number dink dink. Perfect. Okay. So the rest should be fairly straightforward. And we know we also have an eta belt here. We've got an eta fan here. And so on down the road, we're losing power all the way. So equals power in times efficiency power, oops, no, that equals the efficiency. There we go. Now the power going to the fan equals the power coming out of the motor times the belt efficiency. The fan is 65% efficient, so that just equals that number. And so the power at the fan at discharge equals power coming into the fan times its efficiency. Boom. Okay, so I'm going to also do number, no decimals there. Control 1, number, no decimals there. Okay, so as expected, as we move from the motor coming in, power coming into the motor through the system, and again, the system is just this very simple motor belt fan, we lose power to noise and friction and heat and all that good stuff. Okay, so the next thing is pretty much figuring out how much horsepower, how much power is lost at each step. So, well, what's that equal?
Loss.
How many horsepower are we losing in the motor?
The motor, we're losing 7%.
Yeah, we want the number. So here's what he's asking for. We want the units in horsepower. Yeah. So.
Oh, well then, so that's the 137, which is the input.
Yep.
Minus what's going to the belt.
Exactly. So we'll do it in horsepower. So it's actually the 184 minus the 170. Boom. We should be able to actually copy paste. If I copy and paste, and paste again. I don't know if did you see that? I just took this cell, did a copy, clicked here, Control V, clicked here, Control V. So the nice thing about Excel is it does relative references. If I double click this, I can see that E12 is B11 minus B13. If I double click this, even though I never typed any of these characters out, I can see that E14 is B13 minus B15, very cool. And then if I double click here, I can see that this is the cell E16 are the cells B15 minus B17. So the total horsepower lost equals the sum of each of the losses. Close parentheses. And you can double check that over here and just say equals that minus that. So they should be the same, a couple different ways. Nice. Nice. Okay. So, next thing is just how much is being lost at each step. Well, it's just whatever, you tell me which one.
Well, we're just doing percentages, so that would be, the 7%'s lost here, 3%'s lost here, and 35%'s lost there.
That's true. Yeah. So
Correct?
we're losing, but it's a little more subtle than that because we're losing 7% of what came in through the motor, and then we're losing an additional 3%
it's
after that.
compounding.
Yeah. But this guy right here, so we know the total losses are the 76, and the motor losses are 13. So to get that, it's just that percentage. So equals 13 divided by 76. And what I suggest doing here is putting the absolute reference. So divided by click that. Before hitting enter though, let's go back into that formula. Put a $sign before the 18. Okay. Now, what we should be able to do, and then
So now,
we should be able to just. Well, here's the clutch thing about Excel. So if I put my cursor right here in H11 or H12, copy, then put it on H14. And paste, and then paste again. Yeah, and then click there, Control V. Perfect. Now, if we look at this, we can see that. So double click on that cell. Double click on H. Yeah. So that dollar
so
sign.
you're always referencing this, but you're moving it down to this.
Yeah, the numerator is a relative reference, and the denominator is the absolute reference.
Right.
So that helps just sped it up.
Right.
Okay. And then we should also be able to copy here in E18, Control C, and then paste over here in H18, Control V. Control C in E18. I'll first click it, yeah. Control C, click Control V. Because we just copied the sum. So we had all three of those guys, and we need to sum all three of those. So that Control C, Control V worked, and we didn't have to retype the sum, unless you're into that kind of thing. So now I'm going to highlight these 4 cells. Oh, Josh is getting fancy. I was going to do it in one fell swoop. I was going to do control 1 on all of them, and then say that's a percentage. Same difference, and they should add up to. Yeah, perfect. Okay. And then here's the way to think about this total system efficiency. There's a couple different ways to do it. One would be to divide the total, to divide the total losses, which is 76 horsepower, by the total input. We'll do that in a second. But another slicker way is to say this equals, I'm going to say the product of that efficiency, and that efficiency. So I'm coming up with, where's that little button? You got like a percent. Check that out, cool. So the total system is only that efficient. Now, we'll double check that. I'll just say equals losses divided by input oh, I did that backwards, didn't I? Yeah. It's the total power out divided by the input. Yeah, so the 41 was just the difference on that. %, loss, 59% efficient. Okay. So you do the, yeah, you just, so that's how you got to think about those efficiencies. They just keep each one is just a tax on what has already been taxed. Is a way to think of it. Okay. So now, got that part nailed. The next bit, this thing at the bottom is I like to think of this thing at the top as the forward problem, and then the one at the bottom as the reverse problem, or the inverse problem. So now we know that the fluid power at discharge is 155. Fan efficiency is given, so I'm just going to say equals that. Transfer efficiency is whatever this is going on in the belt. And the motor efficiency is given too. So we know that power going into the fan has to be bigger than the power coming out. So that's just going to equal...
No perpetual motion machines.
Oh, man, not yet. It's funny. I keep thinking about perpetual motion, and at some level, it's true, because conservation of energy, you're not getting rid of energy, and conservation of momentum. So in fact, the universe itself is a perpetual motion machine. The problem is humans just keep sending all of this motion at our scale into molecular motion that we can't access anymore. That's kind of the way it is. I mean, still,
You're just turning it into a lower grade.
Yeah, exactly.
Source.
Yeah.
Yeah.
Perpetually degrading it. Yeah. So I guess both camps can win there somehow.
Except the guy with the idea for a machine.
Which one?
Except the guy with the idea for a machine that'll go forever.
Oh, yeah. There's a couple of them out there. I met a few. So number...
I guess you could. As long as you just don't do it in this atmosphere. Sorry.
No problem.
A little sidetracked.
It's all right, it's good. Keeps us safe. So in this case, we're just kind of working back up the ladder. So so we know that we have to put more power in than what came out. So equals that divided by that equals that divided by that. So we're dividing the big number by a number smaller than 1 and getting a bigger number. Is that what we're getting? You might have gone the wrong way on that guy.
Yeah.
Just divide. Yeah. Yeah, because in this case, we're kind of working in reverse.
Right. Building up to.
Yeah, in this problem, we got 155 coming out. You can just write that 150. Going out, so the numbers have to get bigger as we go to the left in the bottom. I'll erase that 184. There we go. There we go. And finally, we'll convert to kilowatts equals that. Kilowatts is going to be smaller, so times 0.746. Enter. So, okay, it's looking pretty good. Control 1. Number. Take. Okay, and then the next problem, so that's looking pretty good. The next deal we're going to do is making it a little prettier. That's just, you're going to get the same answer. It's just rearranging it so that you get some practice running with Excel. All right, so we'll save that.